Hello, everyone. This is Dr. Lennon, and today we're going to talk about L'Hopital's rule. Many of you probably had this in a previous calculus. Usually it happens before Calculus 2, but we're going to touch on it anyway. So we're not going to get into too many of the details or go through any of the proofs. I just want to go through some applications. So what does L'Hopital's rule say? So it's a way to evaluate limits. And really, this O should have like a little mark on top. And it evaluates limits that are in two very specific indeterminate forms. So basically, let's consider a function that's a quotient of two functions. So one thing we need is we need two functions. So let's suppose f and g are differentiable functions. On some interval where we're evaluating our limit. So I'm not going to write down all those hypotheses, but basically on an interval containing a if x is approaching a. So I will write it down. Change my mind. On some interval I containing a, so if one of the two things holds, so if either one, let's say the limit as x approaches a of f of x is the same as the limit as x approaches a of g of x, if those things are both going to 0, or if they're both going to infinity, then what happens is the limit of the quotient is going to be the same as the limit of the derivatives of the quotient. So a lot of times that will allow you to evaluate the limit much more quickly than using some of these trickier techniques that we did when we first started calculus. So then the limit as x approaches a of the quotient of f of x over g of x is the same as the limit as x approaches a of f prime of x over g prime of x. Okay, so can we think of some examples of limits that we evaluated in the past that maybe were tricky, we had to use some heavy machinery for, or some tricky proofs that maybe now can be figured out a little bit easier using this. Let's think about, so one quick example that comes to mind. So let's recall the limit as x approaches 0 of the sine of x over x. This limit we have shown previously, or at least you should have seen in another course, is equal to 1. So usually this is shown by either the squeeze theorem or a geometric argument looking at the ratios of arcs of a circle to a tangent line as you approach 0. So show this using L'Hopital's rule. So not so difficult. So basically the first thing is since the limit as x goes to 0 of the sine of x is the same as the limit as x goes to 0 of x, which both equal 0, basically L'Hopital applies. Right, we've satisfied the necessary hypotheses. So now we can basically say, so thus, when we look at the limit of sine of x over x, this will be the same as taking the derivative of the top and the bottom. So the derivative of the sine is cosine of x, and the derivative of x is 1. So this goes to 0 over 1, which we know is just 0. So excuse me, 1 over 1, which is equal to 1. The cosine of 0 is 1. So 1 over 1, which is equal to 1. So that proves the important limit theorem that we've seen before. So let's look at some examples with polynomials. Again, a lot of times this is helpful with polynomials because their limits will they'll simplify polynomials. Derivatives simplify them. They get a smaller degree as we continue to take their derivatives. So let's go ahead and look at a couple of those examples. So evaluate by L'Hopital's. Rule. Again, I'll speak through why the hypotheses are satisfied, but I may not write them down. So if you were actually writing out a limit argument, you would want to say specifically that the limits are either both going to 0 or infinity, as we did in the previous one. So let's go ahead and look at the first one. And polynomials are always really nice too because they're going to be differentiable over all real numbers. So let's look at the limit as x goes to 1 of x cubed plus x squared minus 2x over x minus 1. So as you can see here, the top is going to evaluate. If you plugged in 1, you're going to get 1 plus 1 minus 2. So the top is going to 0, and the bottom will be 1 minus 1, which is always also going to 0. So this will be the same as the limit as x goes to 1 of 3x squared plus 2x minus 2 over 1. And then we can apply then we can plug in the number because the bottom is no longer going to 0. So if we plug that in, we get 5 minus 2 divided by 1, which gives us a value of 3. Okay. So let's do another. Let's look at the limit as x goes to 0 of the square root of 9 plus 3x minus 3 over x. Again, we see that this is going to be essentially the square root of 9 minus 3, which is 0 on top and 0 on the bottom. So L'Hopital's rule is going to apply here. Furthermore, this is one that maybe we could have done in the past using a conjugate rule, but perhaps it's going to be easier to just apply L'Hopital's rule as we saw before. So let's see how to do that. This is just going to be the limit as x goes to 0, and the derivative of the top, we're going to get 3 times a half, so we're going to get 3 over 2 times 9 plus 3x to the negative 1/2 power, and then the denominator is just going to be 1. So let's rewrite this a little more neatly as the limit as x goes to 0 of 3 divided by 2 times the square root of 9 plus 3x. So now we can plug in 0, so we're going to get a value of 3 over 6, which is the same as 1/2. So that's our limit there. Again, a little bit easier probably than using some of the original limit tricks that we'd seen in the past. Okay, let's try another. Let's look at the limit as x approaches 0 of e to the x minus 1 over x squared. So we see the top is just going to 1 minus 1, which is 0. The bottom is also going to 0. So again, L'Hopital's will apply. So taking derivatives, we're going to get e to the x minus 1 on top and 2x on the bottom. Again, this is going to 0 on top, but it's also still going to 0 on the bottom. So what that means is we can actually just apply L'Hopital's rule one more time. So we get the limit, the derivative of the top now becomes e to the x, and the bottom becomes 2. And now we don't have the evaluation problem that we had in the previous step, so we can plug in 0, and we also get that this limit comes out to 1/2. So let's all of those examples were 0 over 0 examples. Let's go ahead and look at the other indeterminate form, maybe where we have infinity over infinity, something like that. So part D, let's say we're evaluating the limit as x goes to infinity of 4x cubed minus 6x squared plus 1 over 2x cubed minus 10x plus 3. This one, I might say that it's actually easier just to use the previous theorems that you may have learned, where you just look at the dominant term, 4x cubed over 2x cubed. So probably already you can tell that this is going to 2. But using limits, essentially as long as there are x's in either the top or the bottom, we're going to end up with the form infinity over infinity. So L'Hopital's rule will continue to apply. So this will, if we want to go using L'Hopital's rule, we're going to have to take 3 derivatives before we end up in a form without x's. So let's go ahead and do that. We start by getting 12x squared minus 12x over 6x squared minus 10. Then taking the derivative one more time, we end up with 24x minus 12 over 12x. And then taking one last derivative, we see we're getting 24 over 12, which gives us our limit value of 2 that we kind of already recognized would happen. Okay, so sometimes we'll see other forms, so other indeterminate forms. So just a remark. So indeterminate forms are limits that just generally don't evaluate. So there's lots of them, right? 0 over 0, infinity over infinity, 0 times infinity, infinity minus infinity, 1 to the infinity even. So a lot of times what we can do is rewrite these other indeterminate forms in terms of 0 over 0 or infinity over infinity. So other indeterminate forms. So, e.g., 0 times infinity, infinity minus infinity, etc., can often be rewritten using algebra so that L'Hopital's rule will apply. So as I've said in the past, the hardest part of calculus is often getting the algebra right, and the same holds true here. So let's go ahead and look at such an example, or maybe a couple. But let's evaluate, say, the limit as x goes to infinity of x squared times the sine of 1 over 4x squared. So currently, what is going on here? Well, certainly x squared is going to infinity, and 1 over 4x squared is essentially going to 0, so the sine of 0, as we know, is also going to 0. So what we have here is the form infinity times 0. So note that the above is in the form 0 times infinity, or technically infinity times 0, which is the same thing because multiplication is commutative, but I just want to make sure that you recognize which term I'm identifying. So what we can do is actually, the trick here is not so difficult, but we can actually turn this into a infinity or a 0 over 0 form, because often infinity can be rewritten kind of as a 1 over 0 type of deal. So the trick is to realize x squared is the same thing as 1 over x squared. And this term looks like 1 over 0. So basically our limit now is, the limit as x goes to infinity of the sine of 1 over 4x squared over 1 over x squared. And now this thing has the form, we're in the 0 over 0 form, so L'Hopital's applies. Which is what we wanted. So now we can go ahead and take derivatives, and hopefully that simplifies into something where we're going to be able to apply the, or evaluate that limit. Okay, so again, we've got some chain rules going on here. So this is the limit as x goes to infinity, and well, we know the derivative of the sine is going to be cosine, so this is cosine of 1 over 4x squared inside here. And then what's coming out from taking the derivative of the inside? Well, it's 1/4 times x to the negative second. So we're going to get a negative, so we can think of the 1/4 as a coefficient. So we'll have that 1/4. And then what would the derivative of x to the negative 2 be? Well, it would be negative 2 times x to the negative third. And the bottom, we're taking the derivative of x to the negative second, which is going to be negative 2x to the negative third. So we're going to get some cancellation of both of these things here. And then we know that the cosine of 0, 1 over 4x squared, is going to go to 0 here. The cosine of 0 is just going to be 1. So we're going to get 1 times the fourth, and that's what our limit evaluates to, is 1/4. So that's it for here. Okay, why don't we look at one other indeterminate form that is maybe a little bit different. This one is actually of the form 1 to infinity. So there's lots of these things, and often they'll have different tricks. But let's just do one more so you see another trick. So evaluate the limit as x goes to infinity of 1 plus 1 over x to the x power. So what is the form here? Well, inside the parentheses, that's just going to 1, and the exponent's going to the infinity. So note the above has form 1 to the infinity. So what is the trick here? Well, basically what we want to do is, we can't figure out this limit, so maybe we can figure out what the limit of the natural log of the thing is. So let's go ahead and try and do that. So let's try to find the limit of the natural log of the quantity. And then if we know that, then we could exponentiate by e and get the limit that we're after. So let's go ahead and try and do that. So the limit as x goes to infinity of the natural log of 1 plus 1 over x to the x. Okay, so by rules of logarithms, we can bring the x and the exponent out in front, so that's helpful. So the limit here is x going to infinity of x times the natural log of 1 plus 1 over x. And how is that helpful? Well, what is the form we have right now? Well, we have infinity times the natural log of 0, and what are we going to do? Well, that doesn't look helpful, but again, we can use the trick of writing x. So we can write this as the limit as x goes to infinity of the natural log of 1 plus 1 over x over 1 over x. And again, this is because the same trick we used in the previous problem, x is equal to 1 over x. Okay, so what has that done for us? Well, we know the top is going to the natural log of 1, which is 0, and now the bottom is also going to 0. So we are in the form 0 over 0, so L'Hopital's rule will apply. So this is going to be the limit as x goes to infinity of, well, the top, the derivative of the natural log is going to be 1 over 1 plus 1 over x times the derivative of the inside, which is just the derivative of x to the negative 1, which should be minus x to the negative second power. And then the bottom, we're going to get the same thing, right? Because we're just taking the derivative of 1 over x. So we're getting minus x to the minus 2. So those go away. So this limit is essentially just evaluating to 1. Okay, so since this limit evaluates to 1, that tells us the original limit should evaluate to e, because we can just exponentiate to figure it out, right? So since this limit evaluates to 1, the original limit must be e, right? Because the only thing the natural log of a quantity could evaluate to 1 is e, right? The natural log of e is the only value that gives 1. So that's exactly what we have there. And probably when you studied compound interest, you'd looked at this limit before and realized that it had a value of e. Usually they show that and use some numerical analysis to do it. But again, L'Hopital's rule comes to the rescue here. So that's it for L'Hopital's rule. If you've seen it before, it's probably pretty easy. Usually the trickiest parts are if you get some of these indeterminate forms using the algebra to rewrite them. All right, so this is Dr. Lennon signing off.